Hello, this is the next video in a playlist that I'm calling Probability Measure, and we're going to look at an extension of the second Borel-Cantelli lemma by these two individuals here. Now the lemma states this: let A1, A2, be events in a probability space such that the infinite, the series or the infinite sum of the probabilities of AN go to infinity. And this lemma infimum of this quantity here equals 0, then the probability, the limit supremum of AN equals 1. And it's an extension because in the second Borel-Cantelli lemma, this piece right here is replaced with the A1, A2 are independent events. So let's prove this. We're going to prove it in a few steps that seem unrelated, but they're not. So stay with me. So first of all, we want to show the limit infimum of this probability is equal to 0. Then a few notes before we start though, that this I to the AK, so this is an indicator function that either a 1 or 0, and it's a 1 when the event is in AK. And this is absolute value. So note that the expected value of this sum is, you can take the expected value in, and then the expected value of an indicator function is, it only takes on two values, a 1 or a 0. So it's 0 times the probability of that 0 happening, or which is 0, and 1 times the probability that this event happens. So it's 1 times the probability of P A of K. So it's the sum of those probabilities. Now here, this is Chebyshev's inequality. So the probability that x is greater than epsilon is less than or equal to the expected value of x squared divided by epsilon squared. So this is Chebyshev's. We're going to make use of those. Oh, one more note. The variance of IK, the sum of the IK is the expected value of that sum squared minus the expected value quantity squared. Well, this here is a double sum, so you have indicator IJ, times indicator IK. So it's the probability, and the expected value is, the only way it can be a 1 is if they're both 1. So it's the intersection of those events. So that's what we get here. So that's what this piece represents. And then we noted before that that's the sum of the probabilities, quantity squared. So then this right here is, if this is x and this is the minus this quantity, but this is the mean of this quantity, right? So the expected value is that. So when we look at Chebyshev's, the expected value of this quantity squared, but then this is the variance. That's the definition of the variance. And so then you take this squared, so 1/4, then that squared. So that's equal to this. So the variance is this piece right here, right? So if we put this piece over here and this piece over that one, we get this, right? So those cancel on this piece, and then this comes down. Well, we get the double sum of that divided by the quantity squared minus 4. 1 divided by 1/4 is 4. But now if we take the limit supremum of both sides, this function, then by assumption this equals 1, right? So we get 4 minus 4, which is 0. And then that's what we wanted to show, that the limit infimum of this is 0. Okay, so we have that result first. Now let's let dn represent this probability, and n comes into play. That's what we're summing to. That's where the n is. Now again, this is an indicator function, and this is minus 1/2 the sum of the probabilities. Now notice that it's less than or equal to this quantity, and it's not 100% obvious where that comes from. But notice the absolute values here. When you take the absolute value of something being greater than or equal to this quantity, then this in here can be greater than this quantity, or the negative of it can be less than that quantity. And so this piece here is actually just one of those components, and then we're adding in the other. So we have twice the space here as we do here. So this has to have a larger probability. Now by 1, we know that the limit infimum of dn, which is less than or equal to this, and probability has to be greater than or equal to 0, but the limit infimum of this goes to 0, so that means the limit infimum of dn is 0. Now, since the limit infimum of this sequence, remember this dn can bounce around, but the limit infimum says that it has to, infinitely many values have to be within, 0 plus epsilon. I mean, it has to be really close. And so because of this, we can find a subsequence dn such that the subsequence sums to something less, to a finite value. And this is one of those things, it's like, how far do you go back in a proof, till you keep proving something and proving something. But this is a common property of when the limit infimum is 0. Because you can, it says infinitely many of these are 0 or within epsilon, so really small. So you just wait until you get a 0, and wait till you get a 0, and you take that subsequence, and it has to be finite. Now, so that means by the Borel-Cantelli lemma with probability 1, this sequence only happens for finitely many values, right? So since this sum is finite and dn is this quantity here, right? So if it were infinity, that says that this would happen infinitely often. But since it's finite, it says this event, it doesn't happen infinitely often. So that means at some point it has to stop. So it can only happen for a finite, finite number. Could be really large, but we know that for fact now. So hence, for j large enough, then the event reverses. So then this has to happen, right? Because it's only this for finitely many terms. Boom, and then eventually we get to this. Now, since this sum of the AKs, when one goes to infinity, is infinity, by part 2, it says this limit supremum is 1. And that's by the Borel-Cantelli lemma. And so we've proved it. Now, one note here is how, to show that it's an extension, that the limit infimum condition in this lemma, the extension of the second Borel-Cantelli lemma, above is satisfied if the ARs are pairwise independent. And so let's prove that. So this quantity here, remember this was the, if the limit infimum of this is 1, then the theorem holds. And we're going to show that, that if the A's are pairwise independent, then it does hold. Now this step here is actually 2 steps, and I'll try to explain it. And I wanted to, the reason I did it was I didn't want to go over to 3 pages. So let's try to explain this. So when we look at this double sum, we're going to get all possible probability of AJ intersect AK. And at some point, J is going to, K is going to equal to J. So we get the probability of AJ intersect AJ, which is just AJ. So if we take this double sum and leave out the case that J is equal to K, then we get this here. So this sum is from j equal 1 to n, k equal 1 to n, and j not equal to k. That's this piece here. Now, I didn't write that, but now if we want to, and now we can break these apart because they're independent. Then if we want to add back in the case that j, when j equals to k, when we have this product, then we add it here and we have to subtract it here, right? So this does equal the numerator here. And then we just carry along the denominator. Now, let's put this piece over here and then this piece over this piece. And that's what this next step represents. Now this here, since there's no k here, it can actually be taken out here, and then it's the sum times the sum, which is actually a sum squared, right? That's where we get this. And here, it's k equals 1 to n, so we can just put it under one sum, but then factor out one of these probabilities, and that's what we do here. Now notice that probabilities are between 0 and 1, so this quantity here is always between 0 and 1, and when you multiply a number between 0 and 1, it gets smaller. So if we just take this off, then the sum gets bigger, and that's what we do here. So this is 1, and then that is this sum, but one of those cancels with one of these, and then because the sum, by assumption, if we let n go to infinity, this goes to infinity. So 1 over infinity is 0, and so it limits to 1. And so then, if we take the limit and femum of both sides, then it has to be 1. And the condition of the theorem is met. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.